A question. Good morning. Today we are going to continue learning oscillations, and particularly damped oscillations. And we obtained on our last lesson we have obtained that differential equation of damped oscillations can be written in this way. Second derivative of coordinate by time plus plus 2 beta, where beta is damping coefficient multiplied by first derivative of coordinate by time plus natural frequency to the power of 2 multiplied by x, and this is equal to 0. This is equal to 0. And we have, and before this we have learned three small undamped oscillations. If oscillations are undamped, we have differential equation. That we have already solved. d2x by dt2 plus omega 0 to the power of 2 multiplied by x, and this is equal to 0. This is equal to 0. And we have solved this equation. And we have proved that the solution can be written in this form. Xm amplitude multiplied by cosine of omega 0 t plus alpha. I hope you can remember this from our previous lessons. And this is a differential equation of small damped oscillations. Damped means that there are energy, there are leaks of energy. There is dissipation of energy because we have some resistance in system. There are some forces that try to prevent the system, to prevent oscillations in system, and because of these forces we have damping. Because of these forces we have this term. And on our last lesson, we tried to use substitution. We wrote that x is equal to gamma multiplied by y, and this is equal to e to the power of beta t y, where gamma is equal to e to the power of minus beta t, the power of minus beta t. And after this substitution, we have obtained that we have obtained differential equation that can be written in this way: dy second derivative of y by time plus open bracket omega 0 to the power of 2 plus 1 divided by gamma 1 divided by gamma second derivative gamma by time and plus 2 beta divided by gamma first derivative of gamma by time, y, and this is equal to 0. This is equal to 0. Okay, so let's simplify this equation. We need to simplify the expression in brackets. To do this, I'll rewrite this expression. Here, gamma by dt 2 and plus 2 beta divided by gamma d gamma by dt. So we need to simplify this expression. To do this, let's find that 1 divided by gamma is equal to 1 divided by e to the power of minus beta t and what about first derivative d gamma by dt is equal to minus beta e to the power of minus beta t. And the second derivative, d2 gamma by dt to the power of 2. And this is equal. This is equal. This is equal to beta to the power of 2 e to the power of minus beta t. Minus beta t. Minus beta t. Okay, let's use this here. Let's use this here. So this will be omega 0 to the power of 2 plus 1 divided by e to the power of minus beta t minus beta t multiplied by beta to the power of 2 e to the power of minus beta t plus 2 beta divided by e to the power of minus beta t minus beta t and multiplied by minus beta e to the power of minus beta t. Oh, it will be equal to omega 0 to the power of 2 omega 0 to the power of 2 plus beta to the power of 2 minus 2 beta to the power of 2. And this is equal to omega 0 to the power of 2 minus beta to the power of 2 minus beta to the power of 2. Okay, do you have any questions? Do you have any questions? No questions. No questions. Okay. If there is no questions, I will clean some unnecessary information from the screen and I will leave only the result what we need. Only result what we need. So we have proved that this expression in brackets is equal to omega 0 to the power of 2 minus beta to the power of 2. And from here we have equation d2y second derivative of y by time plus omega 0 to the power of 2 minus beta the power of 2 in brackets y, and this is equal to 0. This is equal to 0. This is equal to 0, and we can make we can use some new signation. We can use some new signation. We can write this as omega v is equal to omega 0 power of 2 minus beta the power of 2 under the square root So after using this signation here, we have obtained that this is equal to d2y by dt 2 plus omega v y, and this is equal to 0. This is equal to 0. Okay, do you have any questions? Do you have any questions about this? No questions. Okay. If there is no questions, I will use this. I will use this, and here we don't need this anymore. So we have proved that such substitution leads to this differential equation. But this differential equation is very similar to the differential equation in the red frame. It is very similar to differential equation in the red frame. So according to this, we can find the solution that according to this y is equal to xm cosine omega v multiplied by time plus alpha and x is equal to e to the power of minus beta t multiplied by y, and this is equal equal to xm multiplied by e to the power of minus beta t multiplied by cosine of omega v t plus alpha. Okay, this is the solution. This is the solution of three small damped oscillations, or of differential equation of three small damped oscillations. Okay, what questions do you have about this? What questions do you have, or no questions? If there are no questions, we can clean some information from the screen. We can clean some information. We can clean some information. Clean some information from the screen. So we have solved this equation. Solved this equation. Here we have if we are considering that omega zero is more than beta. So natural angular frequency is more than damping coefficient. Is more than damping coefficient. We are considering this case. When omega zero is more than damping coefficient. So in this case, the solution is here. The solution is here, where angular frequency of damped oscillations, frequency of damped oscillations, and we can also write period of damped oscillations. T is equal to 1 divided by linear frequency, and this is the same as 2p divided by omega v, and this is the same as 2p divided by square root of omega 0 to the power of 2 minus beta to the power of 2 minus beta to the power of 2 minus beta to the power of 2. Okay, so do you have any questions? Do you have any questions? About this differential equation? Okay, maybe let's try to build a graph of this dependence. I'll draw a coordinate system. I'll draw some coordinate system in this way. For example, here we have 0, 0 time coordinate x coordinate, and here we can draw these two dash lines. I'll make it dash. I'll make these lines dash. I'll make these lines dash. And this is xm. And this is xm multiplied by e to the power of minus beta t. And here minus xm e to the power of minus beta t. And we can draw a graph of damped oscillations. This is this dependence. This dependence is shown on this graph. Okay, and according to this graph, we can write. We can use a new value that is known as amplitude. Amplitude of three small damped oscillations. Amplitude of three small damped oscillations. It can be written as a is a function of time, and this is equal to x maximum value of coordinate, maximum initial value of coordinate multiplied by e to the power of minus beta t. To the power minus beta t. Okay, do you have any questions about this? Do you have any questions? Do you have any questions? Okay, no questions. No questions. And if there is no questions, if there is no questions. If there is no questions, I think I will clean this from the screen. I'll clean this from the screen, and we can consider, we can learn one characteristic of damped oscillations. I mean logarithmic decrement. Logarithmic decrement. Logarithmic decrement. Logarithmic decrement. I'll write this. Logarithmic decrement. Logarithmic decrement. Logarithmic decrement. This value is equal to natural logarithm of a of t divided by a of t plus period. T plus period. And this is equal to logarithm xm, logarithm xm xm e to the power of minus beta t divided by xm divided by xm multiplied by e to the power of minus beta t plus period. T plus period. And this is equal to logarithm e to the power of minus beta t plus beta t plus period. And this is equal to natural logarithm multiplied by e to the power of beta t. And this is the same as beta. This is the same as beta t. This is the same as beta t. The same as beta t. Okay, do you have any questions about this? No questions. No questions. Okay, if there is no questions, I will clean some information. So we can write that this is equal to beta t. This is equal to beta t. And logarithmic decrement may be written in another way. So let's consider this expression. A amplitude on time t, amplitude on time t plus n, t plus n multiplied by period, when where n is some natural number, so n is equal to 1, 2, 3, 1, 2, 3, and etc. So it will be equal to logarithm uh, of xm e to the power of minus beta t divided by xm e to the power of minus beta t plus n t plus n t and this will be equal to natural logarithm e to the power of minus beta t plus beta t plus n t, and this will be equal to natural logarithm e to the power of n beta t, and this will be equal to n beta t, and this is the same as from here. This is the same as n multiplied by logarithmic decrement. Okay, so do you have any questions about this? Do you have any questions about this? No questions. No questions. If there is no questions, we can write that this is n multiplied by logarithmic decrement, and from here we can find that this will be the same as 1 divided by n natural logarithm a as a function of t divided by A as a function of t plus n t plus n t, and this is equal to beta t. This is equal to beta t. It is necessary to write this here. It is necessary to write this here in this frame. Okay, so do you have any questions about logarithmic decrement? About logarithmic decrement. It shows logarithmic decrement. Logarithmic decrement shows how fast damping is. How fast damping is. Damping decrease in amplitude. Decrease in amplitude of damping oscillations. And what is necessary to say? What is necessary to say? We have learned case when omega 0 is bigger than beta. When natural case when natural frequency is more than damping coefficient. But what if we have case? What if we have a case of equality, or if we have angular frequency, natural angular frequency is less than beta. We can see that in this case, period of oscillations in this case, period of oscillations does not exist. So in this case, we can write that if this or this, we can write that damping oscillations, free damping oscillations, are impossible in these cases. So we can maybe frame this in blue, and it is necessary to say that this case is known as critical damping. This is critical damping, and this case is over damping. is overdamping, and respectively this case is underdamping. Sometimes you can see such words in the internet. Okay, do you have any questions? Do you have any questions about this? No questions. There are no questions. Okay, if there are no questions, uh, one more important value for damping oscillations, for damped oscillations is quality. Quality of damped oscillations. This is Q. Q quality. Q is equal to P divided by logarithmic decrement. Logarithmic decrement. Quality is value that shows the ability of oscillator to keep its energy. It shows the ability of oscillator, or the ability of oscillation system to keep its energy, to keep energy of oscillations. Oh, and according to this, this is equal to P. This is equal to P divided by beta T, and this is equal to omega V divided by 2 beta. Divided by 2 beta. So this is quality. This is quality. This value is sometimes this value is very important in for telecommunication equipment, for radio techniques, for receiving signal, transmitting signal, and in many cases, we have situation when we have this condition. If omega zero is much bigger than natural angular frequency is much bigger than damping coefficient. In this case, we can write that omega v is equal to square root of omega 0 to the power of 2 minus beta to the power of 2, and this will be almost equal to square root of omega 0 to the power of 2, and this will be absolute value of omega 0 but an angular frequency is always a non-negative value, and because of this we can write that this is equal to omega 0. This is equal to omega 0. And this means that in this case we can write that quality is equal to omega 0 divided by 2 beta. Divided by 2 beta. Divided by 2 beta. Okay, what questions do you have about this? What questions do you have about this situation? No questions. No questions. Okay, if there is no questions, uh, let's begin to learn. Let's begin to learn forced small oscillations. Forced oscillations. We are starting to learn forced oscillations. And for example, we will consider a simple oscillator, but with internal periodical force, with internal periodical force. Oh, let's draw this. Let's draw a picture. So here we have wall, and here we have a spring connected with mass, m, with mass. Here we have spring constant, some coefficient of dissipation, and here we also have some internal, some external periodical force, external in relation with the simple oscillator, some external periodical force, Fm cosine omega t, cosine omega t. So for a simple oscillator, we have that acceleration is equal to first derivative of velocity by time, and this is the same as second derivative of coordinate by time. Here we have that force that is impressed on mass M. Force is equal to minus k x. This is a tensile force. Tensile force minus force of resistance. Force of resistance. This is equal to dx. Some coefficient of resistance multiplied by first derivative of coordinate by time, and plus Fm multiplied by cosine of omega t. Cosine of omega t. So we have acceleration, we have force. So to build dynamics equation, we can use the second Newton's law. Second Newton's law of the motion. Second Newton's law of motion. We can use here. According to this law, mass multiplied by acceleration, is equal to force. I have written second Newton's law of motion in projections on the direction of the motion. So I have written it without vectors. Without vectors. So we have differential equation. M multiplied by second derivative of x by time and this is equal to minus k x minus mu dx by dt plus fm cosine omega t. Cosine omega t. And we can make some algebraic transformations. And obtain that. And obtain differential equations of forced oscillations. Dx by dt to the power of 2 plus mu divided by m dx by dt plus k spring constant divided by mass multiplied by x and this is equal to f m divided by m and multiplied by cosine omega t. Do you have any questions about this? Do you have any questions? No questions. No questions. Okay, if there's no questions, we can rewrite this equation in this way. d2x by dt the power of 2 plus 2 beta dx by dt dx by dt and plus omega 0 to the power of 2x, and this is equal to fm divided by m cosine omega t. Cosine omega t. What questions do you have about this? Where beta damping coefficient is equal to mu divided by 2m, and omega 0 is equal to omega 0 is equal to k divided by m under the square root. Okay, do you have any questions? Do you have any questions? No questions. No questions. Okay, so I can clean some unnecessary information from the screen. And we can make a conclusion that for forced oscillations in simple oscillator, we have differential equation. We have differential equation that can be written in this way. So simple oscillator. In the case of torsional pendulum, physical pendulum, or simple pendulum, the differential equation of small forced oscillations will be very similar. It will be very similar to this. Will be very similar to this. Oh, okay, and solve. I hope we will solve this equation. Next week. We will solve this equation next week, and now it is necessary. Now it is necessary to learn electric forced electric oscillations in so-called RLC circuit. What is this? What is this? This is a circuit that that contains resistor R, resistor connected with inductor, connected with inductor, and connected with source of electromotive force. Some electromotive force generator. That can be shown in this way. And here we have capacitor. Here we have capacitor. Here we have capacitor. Necessary to write this properly. What's wrong with this? Here we have capacitor. Here we have capacitor, and this is connected to resistor. This is connected with resistor. Okay. So this is resistance R, inductance L, capacitance C, and electromotive force E. Where electromotive force E is equal to EM multiplied by cosine of omega t. Cosine of omega t. So let's build differential equation of electrical oscillations in this circuit. To do this, let's remember Ohm's law. According to this law, we can remember that electric current is equal to electromotive force divided by sum of external and internal resistances. So from here we can write that electromotive force is equal to I multiplied by R plus some resistance multiplied by electric current. Multiplied by electric current. And here it can be signed as UR. UR. So this is voltage across resistance R. Voltage across resistance R is signed as UR. So according to this, we have that electromotive force is equal to voltage on resistance R. In very similar way, we can do for our RLC circuit. In a similar way, we can write that this is electromotive force plus electromotive force of self-induction, and this is equal to voltage on resistance plus voltage on capacitor. Okay, do you have any questions about this? Do you have any questions about this? No questions. No questions. So here we have forced oscillations. Oscillations in a simple oscillator. In a simple oscillator. Forced oscillations in a simple oscillator. And here we have forced oscillations in a RLC circuit. Okay, let's build this differential equation. From our previous lessons, you can remember that electromotive force of self-induction is equal to minus inductance multiplied by derivative of electric current by time. Where electric current is the derivative of electric charge by time. The derivative of electric charge by time. So this is equal is minus L d to q by dt 2. Okay, what about voltage across resistance? Voltage across resistance, it is equal to resistance multiplied by electric current. So this is R cos derivative dq by dt by dt. And what about voltage across capacitor? We can remember formula that charge of capacitor is capacitance multiplied by voltage across this capacitor. According to this, we have that U C is equal to Q divided by capacitance. Electric charge divided by capacitance. Okay, so do you have any questions about this? Do you have any questions? No questions. Okay, if there is no questions, I will remove some unnecessary things. I will remove some unnecessary things. I will remove some unnecessary things. And okay, let's use this formula here. So let's make substitution and obtain differential equations. So this is equal. This will be EM cosine omega t minus L d2 u by dt 2, and this is equal to R dq by dt and plus q divided by c and from here we have that d2q by dt 2 by dt 2 plus R divided by L dq by dt and plus 1 divided by L c q, and this is equal to em divided by L cosine omega t Okay, do you have any questions? Do you have any questions? No questions. No questions. Okay. So I will clean some things from the screen. We have already had differential equations of forced oscillations in RLC circuit. So it can be this can be written in another form, in another useful form. It can be written d2q divided by dt to the power of 2 plus 2 beta multiplied by dq by dt plus angular velocity or natural angular frequency to the power of 2 multiplied by q, and this is equal to em divided by L cosine omega t, where beta is damping coefficient, and this is equal to R divided by 2L. And omega 0 is equal to 1 divided by square root of LC. Square root of LC. Okay, do you have any questions? Do you have any questions? No questions. Okay, so as you can see, differential equations for small forced oscillations in a simple oscillator or in a RLC circuit, these differential equations are very similar. They are very similar, and it means that they may be solved together. And I hope we will do this. We will do this on our next lesson. Okay, do you have any questions? Do you have any questions? No questions? Okay, if there are no questions, so thank you for your attention. I hope to see you next week.